Okay, so this lecture is about KSP, the solubility products. When we talk about solubility products, we're talking about a solid and the ratio at which it will ionize in water. Now, if we look at barium sulfate, which is a solid, we would see that normally barium sulfate would break down into its ion, Ba2+, and the sulfate anion, SO4 2-. So these are what it would break down into to become an ion. The question is, how much does it really break down? How much does it truly ionize? So when we talk about that, we talk about it in terms mathematically of the equilibrium constant expression for this, which is KSP, which is just another new K constant that we have. So far we've had KC, KP, KA, KB. Now we're going to have KSP. So each individual solid has its own value of KSP, just like each acid or base has its own Ka or Kb value. And because we ignore solids and liquids, we're only going to be looking at the anions. So in this case, for this particular reaction, its KSP would be equal to each of the ions taken to the power of their coefficients. In this case, it's all a 1-to-1 ratio. So it's simply KSP equals the barium ion concentration times the sulfate ion concentration. So if we look at solubility products, there's a couple of things you need to keep in mind. KSP is not the same as solubility. Okay, solubility is solubility. How much does something dissolve into water? KSP is a relationship. Solubility is generally expressed as a mass divided by the volume. So we can say that, or we can say it in terms of molarity. So we can either say grams per liter, grams per milliliter, or moles per liter. But there's always that compound unit, and you know which one to use based on the information you're given in the problem. If you're given moles, you're going to use molarity. If you're given grams, you're going to use either liters or milliliters, depending on what you're given. So what is going to affect solubility of these solids? Some solids are very readily soluble in water, such as sodium chloride or sugar, but some things are not. They'll only partially ionize, just like we see with weak acids or weak bases. So one of the things that can affect them is what's called the common ion effect. You saw about that in the last video lecture I put out. So if there's already some of I'm losing my train of thought, sorry. If there's already some of the anions in solution for whatever reason, if there or the cation, if there's a common ion already in solution, then that's going to decrease the solubility. Okay, if I already have some of this in solution and I add more to it, increasing these, that's going to cause the shift back to the left and decrease the solubility of the solid. Remember Le Chatelier, shifts. Okay, pH factors. If something has a basic anion, it's going to be much more soluble in an acidic solution. If it's got an acidic anion or cation, it's going to be much more soluble in basic solutions. So keeping in mind what you have is going to be very important. So if you look at these two examples here we have a salt for the first one. It says the salt whose anion is a conjugate base of a weak acid. So if we have a weak acid, then this perhaps came from HF. HF is a weak acid, therefore it is a strong base. Okay, so if it's a strong conjugate base, then the solubility will increase as the solution becomes more acidic. Here, if we have the base of a strong acid, we're going to have no effect. Okay, solubility does not change, excuse me, by the changes in pH. All right. So if we added hydrogens to it, meaning making it more acidic, then we would see it's not changed. The solubility doesn't change. If we made it more basic, it would change. Other factors that affect solubility are what we call complex metal ions. These are just very, very complicated structurally. We're not going to get into it. You don't need to understand that. You just need to know that if I ask about complex metal ions, what's going to happen. So complex metal ions have the metal in the center, and it is surrounded by very large, complicated things with bonds that you haven't even heard of yet, so I'm not going to get into that. But we call those attachments to the central metal atom ligands. Ligands, ligands. It's just a fancy name to say attachments. All right. So what happens is these complex metal ions, the metal in the center, can act as a Lewis acid and form more complex ions with Lewis bases in the solvents. So it just becomes very complicated in the structure. If you kind of look at these examples here of what's happening, if, for example, your complex ion is this first one, all right, and what I see happens is it breaks down. These can often form more very complex Lewis bases in the solvent, so it'll dissolve more. Other factors, complex ions. If we form these complex ions, we're going to see changes. All right, so that's another thing. If we just had, for example, here silver chloride, and it reacts with NH3 and forms this complex metal ion, we're going to increase the solubility of the salts. So the KSP increases. Amphoterism, basically all that means is that metal oxides and hydroxides, they can behave like an acid in a basic solution, and they can behave like a base in an acidic solution. So when we have amphoterism, meaning they can behave as either one, their solubility increases. So if we have these are just some examples of common cations that can behave as both an acid or a base. When we have one of those present, it increases solubility. So will a precipitate form in these reactions here? Well, we know what's going to happen based on the reaction quotient versus K. Remember, if you go back, K is at equilibrium and Q is any point outside of equilibrium. We can calculate the concentrations mathematically the same way as K, but Q tells us at any given point when the reaction is occurring, not necessarily at equilibrium. So if I look at Q equals K, that's when our system is at equilibrium. And you got to remember Q, because it is also products over reactants. If you just kind of think about this mathematically, well, if Q is very small, mathematically, that means this number is very large, because 1 over a large number is a small value, right? It's a decimal. If this is very large, that means Q is going to be large. Okay? Because a large number over 1 makes Q large. All right? So kind of keep that in mind mathematically. So when Q is equal to K, the system's at equilibrium. If Q is less than K, smaller, all right, that means more solid can be dissolved until we get to this point of Q equaling K. If Q is greater than K, the salt will precipitate out. So you can kind of think about it like unsaturated, saturated, supersaturated. Okay, so this would be our saturated. Let me change colors here. So this would be saturated. This would be unsaturated. and this would be supersaturated. Okay, so if we have something at equilibrium, everything that's in solution can already be in solution. If we have Q less than K, we know that more solid can be dissolved until we meet that equilibrium point. And if Q is larger than K, the salt is going to precipitate out until we get to equilibrium, where Q is equal to K. So if we look at the differences in solubilities of salts, we can see what's happening, okay? So if we just go through this flow chart, what we'll see is there's kind of what we call selective precipitation of ions. So if we have a solution with some unknown metal cation, if we were to add 6 molar hydrochloric acid, what happens? Well, do we get a precipitate, or do we decant out the remaining cations? So if we get a precipitate, one of our choices are these, because we're following our solubility rules. That's how we know it would be one of these 3 choices that precipitated out. Now, if we have our remaining cations and now add hydrosulfuric acid and a hydrochloric acid, then if we get a precipitate, it's going to be one of these. It's going to be one of these insoluble sulfides. How do I know it's an insoluble sulfide? Because I added a sulfide and I've looked at my solubility rules. If that does not, if nothing happens, if I get no precipitate, well, maybe I add now an ammonium sulfide at a pH of 8. Okay, why? Because then if I can figure out which metal containing solution I have, because I might get a base insoluble sulfide and hydroxides. Now what that means is it'll precipitate out because it'll precipitate out in the base that I just added. If I still get nothing, that's when I can add these. And I'm either going to get a precipitate again based on my what I added. So if you can see the anions there, the phosphate, if it precipitates out, these are the metals that make the phosphate insoluble. And if I don't get anything, then I know I have one of the alkali metal ions and NH4+. So rule 1 on the list of your solubility rules, because there's nothing that will make them precipitate out because they're always soluble. There's no exceptions to those. So you can do a little guessing on what would happen, right? Based on your solubility rules and what you know will react to create a precipitation if you have an unknown metal cation. I expect you to understand this only on a understanding level, be able to talk about it and how this works, not anything mathematical. That's it for this lecture. I have already posted one of the 2 videos I told you I would find that would supplement this. This is going to be uploaded in a few seconds. If you're watching it, it already has. And then I will go and upload the other video later on this afternoon. Bring your worksheets back to class on Tuesday and be ready to work them. Okay? Have a great weekend, you guys.